Hey everyone, welcome back to Math 256. This is Scott. Let's get started. So what we are going to be looking at now is section 4.2, which your book calls forcing, but which in reality is just actually the subject of non-homogeneous linear equations. Alright, so here's the setup. So what we are going to have is a degree n linear differential equation with constant coefficients. So just as an example, maybe we have something like y double prime minus 3y prime minus 10y. Now if this equaled 0, then it would be homogeneous and we would know what to do. But if it doesn't, let's just say it equals some function f of x, or f of t, I'll say f of t. F of t over here, then that's what makes it non-homogeneous. Okay. So here's our approach. Y equals, and what we're going to do is we're going to break it down into two parts. There is yc plus yp. And what each of these are going to represent is the following. So yc, so this is the complementary solution. And what this represents is the general solution to the associated homogeneous equation. So f of t, if that just equaled 0, in other words, the situation from the previous section, that's what this would represent. So this is the complementary solution. So this is the general solution to the associated homogeneous equation, whereas yp here, this represents what is called the particular solution. Which, as the name suggests, is not a general solution, but is a particular solution, and it is a particular solution for the non-homogeneous equation. So this is a single particular solution to the original non-homogeneous equation. So So YC we know how to find. YC, find this as in section 4.1. Okay, so that one, check. YP, how do we find that? So we find this using a new method we're about to explain. So find using, so we're about to explain a new method here, and it's a bit of a doozy, so buckle up. Find using the method of undetermined coefficients. Alright, so the process here. So undetermined coefficients. Here's how this works. So first off, it's helpful to find YC to begin with. So 1. Find YC first. So if you can find the complementary solution first, then do so. So then step 2. Look at f and consider its derivatives up to the order of the differential equation. So take the derivatives of f from order 0 up to n. And this doesn't have to be done actually explicitly, it can just be done in your head. And then the types of terms. Types of terms, ignoring coefficients, that we produce will be the terms that we assume YP is made of. Alright, so then assign these terms generic coefficients A, B, C, and so on, for however many we have. Then create, let's say create YP in terms of these terms. Take take the necessary derivatives, plug the results into the original differential equation, and then finally solve for the coefficients by grouping together like terms. Then together this will produce the general solution. So then y equals yc plus yp, and this will have constants C1, C2, etc., which we would need initial conditions to solve. Which can be found via initial conditions. Whereas yp here, this one is independent of the initial conditions, and it just represents just the particular solution, and it will have all of its coefficients found. So this one will be made of terms with coefficients found as above. Alright, well then, that's what we are ultimately in the game of doing here. However, there is one extra complication. So there's one little caveat here, so beware. So a complication, and this will come up, so watch out. So a caveat, or a complication, beware. If any of the families of terms in our yp, if they duplicate terms found in yc, we have to disambiguate them by multiplying all the members of the family by a power of t sufficient to clear any duplications. Alright, so it's an awkward thing to word, but it's easy enough to see once you see a couple examples and get the hang of it. It can still be a bit of a hassle, but at least the process is straightforward. But let's just first here explain why this works. So no, let's do some examples first, and then we'll discuss why it works. So let's just see some examples of this in action. So examples. A. Let's just take y double prime minus y prime minus 6y equals t plus 1. Alright, so if I had said equals 0, then this would be just straight out of the pages of section 4.1, and it would be just a regular old homogeneous second order differential equation as we've seen and dealt with before. But now here what we have to do is take the pieces separately. So first let's find the YC, the complementary solution. So here I'm going to just make the characteristic equation r squared minus r minus 6 equals 0. So in other words, we've got r minus 3 times r plus 2 is what equals 0, giving us r equals 3 and negative 2, and giving us a y complementary of c1 e to the 3t plus c2 e to the negative 2t. Alright, so that's how the complementary solution is found. It's just like what we've been doing. Now f of t here is equal to t plus 1. And if I think about what the derivatives of f of t are going to make, so f prime of t is just going to equal 1, f double prime of t is going to equal 0, and so altogether the terms from f and its derivatives will be just t and 1. In other words, if I give them unknown coefficients, it'll be just a of t and b. So these are the only terms that come from f and its various derivatives up to the order of our differential equation. And so then that means that our yp is just going to be something of the form at plus b. Well, so be it. But this is supposed to fit this. And in order to make that happen, we just have to figure out what values of a and b are going to be in play here. So then yp, I have to take the derivative of that if I want to plug it into the equation. It looks like that'll just be equal to a, and yp double prime will just be 0. So I'm looking for the values of a and b that will make this satisfy this equation here. So yp double prime minus yp prime minus 6yp is supposed to equal t plus 1. So then I just put in here the 0, I put in here the a. I put in here the at plus b, t plus 1. Oops, don't forget the 6. Okay, so then what do we have? We have negative a, we have minus 6at minus 6b equals t plus 1. So then if I want to take this, I can break it up into the x terms. Sorry, the t terms, I should say. Yeah, just do it below here, fresh start. Okay, so then I can do the t terms. And that's going to give me negative 6a negative 6a equals just 1, or negative 6at equals just t. I guess we'll write it negative 6a equals 1. So a equals negative 1/6. So be it. Now the constant terms. If we set those equal to each other on both sides of the equation, we have negative a minus 6b equals just 1. But here, I know the value of a, so this means positive 1/6 minus 6b equals 1, which means then if I were to, let's say, add this, subtract that, I'd have negative 5/6 equals 6b, meaning b is equal to negative 5/36. And then that gives me, finally, my yp, which is going to equal negative 1/6 t minus 5/36. So then our general solution by equals c1 e to the 3t plus c2 e to the negative 2t minus 1/6 t minus 5/36. Now, before we take this this method and start applying it to more examples, let's actually start off by discussing in general terms why this works. So why this works. So why this works. So for this specific example, we and it'll be easier to discuss in this context. So yc double prime minus yc prime minus 6yc is equal to 0 by definition. Yp double prime minus yp prime minus 6yp is equal to t plus 1 by construction. And so then, if I were to take them and add them together, I'd have yc plus yp, second derivative of that. Because the derivative, if you remember, it is linear in the sense that if you add together two derivatives, it's the same as the derivative of the sum. And same thing if it's negative. So then minus yc plus yp prime minus 6 times yc plus yp, and that has to just equal 0 plus t plus 1, meaning that anything that is made out of these ingredients will be a solution here. So thus y equals yc plus yp will be a solution. And the reason why it's the general solution is the fact that basically by construction we'll be able to match any pair of initial conditions to a specific value of the constants from yc. But that's a little bit beyond our scope. So it is a solution, and it turns out this is the general form of all solutions because any initial conditions can be tailored to fit this with the c's. Okay, so back to our examples. Let's just take another one on and see where it gets us. So this is just example B in the same series as before. Pardon the interruption, but that's just why it worked. So let's think about this now. So let's go y double prime minus y prime minus 20y equals e to the 2t. E to the 2t. Okay, so here, let's just think about this one and think about what we've got here. So r squared minus r minus 20 equals 0 will be our characteristic equation, which we'll then solve according to the usual methods. So r minus 5r plus 4 equals 0, which leads us to r equals 5, comma negative 4, which leads us to our complementary solution being c1 e to the 5t plus c2 e to the negative 4t. And it doesn't matter which term you write first. The solutions will be equivalent. Alright, now if we look at f of t, we'll have e to the 2t, and f prime of t would then be 2e to the 2t. F double prime of t would be now 4e to the 2t, and no matter how many derivatives one takes, we get terms that are pretty much the same, just with different coefficients. And so that means that the kinds of terms we expect to see here, so yp, we expect to just have terms a e to the 2t. So all the terms here end up being something or other of this form, and that is therefore what we will use. Now you look at it to make sure there's no duplication, and there still hasn't been any duplication, not yet. We'll save that for when we want an extra challenge. But for now, we can now just continue with our process. So we will take then the yp's and their derivatives. So if it's a e to the 2t, then yp prime will be 2a e to the 2t, and yp double prime will be 4a e to the 2t. And then our original differential equation tells us that our yp, if it's going to be any particular solution here, it's going to have to fit this pattern. yp double prime minus yp prime minus 20 yp is supposed to equal e to the 2t. So here, putting all these pieces into play, we're going to have 4a e to the 2t. Here we're going to have 2 a e to the 2t. Here we're going to have 20 a e to the 2t is equal to just e to the 2t. And now all the terms here just have the same basic function. They're all just e to the 2t. So we can just combine them all and see what we get. So we have 4 minus 2 minus 20 is going to be negative 18 a e to the 2t equals e to the 2t. So negative 18a equals 1, which means a equals negative 1/18, which means that our yp is just negative 1/18 e to the 2t, which then means that our general solution is going to be y equals c1 e to the 5t plus c2 e to the negative 4t minus 1/18 e to the 2t. And with initial conditions, we would just find the c1 and c2 accordingly. Now let's see something like this. What if we have y double prime minus y prime minus 12y equals sine 3. This time I'm going to make it an x. Shake things up. So now it's assumed that y is a function of x. Alright, so r squared minus r minus 12 equals 0 is what the left side will imply, which means r minus 4 times r plus 3 equals 0, which means that r equals 4 or negative 3, which means that our complementary solution is equal to c1 e to the 4t plus c2 e to the negative 3t. Over here, if we look at our function f of t, we'll have, f of x. Alright, never mind. I was going to change things up and write it with an x, but now I'm in the habit of writing it with a t, so I'd have to make that an x and that an x, and I'll just switch it back to t, make it more like our usual one. Nothing is different if we use different letters. It's just different notation. So then f prime of t would be then looks like 3 cosine 3t. F double prime of t would be back to sine but negative 9. Not that it really matters. We're supposed to be ignoring these coefficients anyway. Negative 9 sine of 3t. And so then what this means is that our yp is going to be made up of terms that involve a sine 3t, b cosine 3t. We don't worry about these other coefficients. We'll let just the derivatives that we're going to be taking now deal with that. So yp is equal to a sine 3t plus b cosine 3t. And as you get more practice at this, you will basically be able to just immediately jump to the conclusion that if you see one of the sine or cosine, your particular solution is going to have terms from both. And so then that leads us to yp prime is equal to 3a cosine 3t minus 3b sine 3t. Yp double prime, just take the derivative again, and we're going to have now negative 9a sine 3t. And here it's sine, so it's going to become negative 9b cosine 3t. And then from this, we can start to try to solve for the a, b, and c. So yp double prime minus yp prime minus 12 yp is supposed to equal sine 3t. So now we'll just put these pieces into play. A sine 3t plus b cosine 3t minus 3a cosine 3t minus 3b sine 3t minus 12 times negative, oops. I was reading them backwards, looking at them backwards here. Let's just take that from the top, shall we? Well, take it from the bottom. I was taking it from the top. And that's what happens when you get complacent with these. You'll mess up something that shouldn't be that hard. Just put the piece here where it goes here. Negative 9a sine 3t is what I meant to say. Minus 9b cosine 3t is what I meant to say. Minus 3a cosine 3t minus 3b sine 3t minus 12 times, now it's just a sine 3t plus b cosine 3t, and that's supposed to just equal sine 3t. Alright, well, if we are careful here, we can manage to distribute the things that need to be distributed and collect the things that need to be collected. So let's see, negative 9a sine 3t minus 9b cosine 3t minus 3a cosine 3t plus 3b sine 3t minus 12a sine 3t plus, minus 12b cosine 3t is equal to 0 cosine 3t plus 1 sine 3t. Just me expanding the right here so that I can see both the sines and cosines. Okay, so all the cosines here are just going to be equal to 0. So cosine 3t, I know that negative 9b minus 3a minus 12b equals 0. So in other words, negative 21b minus 3a equals 0, which, just for the record, that means then 3a equals negative 21b, which means that a equals negative 7b. Good to know. Probably going to be useful. Alright, now on the sine side of things. So sine of 3t. So that's going to be here, 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 and here. I'm going to have negative 9a plus 3b minus 12a equals 1. So then, if I combine like terms here, I'm going to have negative 21a plus 3b equals 1. Now, this may seem shockingly similar to what we saw before, but notice that the coefficients are all swapped in. We have a 1 here instead of a 0. So I'm not going to be able to just divide everything like I did before, but what I can do is I can just plug the piece here that I have in here. And so I'd get, so if I use this up into here, I'll have negative 21 times negative 7b plus 3b equals 0. And here, for this one, when it's 21 times 7, what is that? That's 147. B, oops, not equals 0, equals 1, plus 3b equals 1, which means that 150b equals 1, which means that b equals 1 over 150. And you get these kinds of crazy coefficients when you're using this method. So, be warned. And then based on the a being, so if I plug that into here, I'd get then a equals negative 7 over 150, which means then that my yp is equal to, and just remind ourselves, was a for sine or for cosine. You look back at this and you see a was on the sine, and so you respect that. So you say negative 7 over 150 sine 3t plus 1 over 150 cosine of 3t. And then that gives us our general solution. So our general solution will then be y equals c1 e to the 4t, what was the rest of it, c2 e to the negative 3t minus 7 over 150 times sine of 3t plus 1 over 150 cosine of 3t. So notice that in the case of different initial conditions, we would end up with different values of c1 and c2, and the values of the yp would not be varying. But again, we have a lot of examples to cover here, and so we can't afford to take an extra detour into the into initial conditions at this exact moment, because in particular we still haven't seen any cases of duplication. So let's take a look at some cases now of duplication. So this was example C, so now example D, where we're going to get our first taste of what happens when we get duplicate terms. So this is going to be y double prime minus y equals e to the t. This is relatively simple looking, but let's just see what happens. So it's going to be r squared minus 1 equals 0, meaning r equals plus or minus 1, which means that the complementary solution here is going to be c1 e to the t plus c2 e to the negative t. Well, that's all well and good, but then when we look over here at f of t and f prime of t and f double prime of t, we keep getting e to the t, and when we look at that, no matter what, this is a duplicate. So what we have to do is we have to take our basic solution here, which we would have put just e to the t right here. This would have been, we would have just put a e to the t. But we disambiguate it by putting in an extra t. And the reason why this will work is the same reason why it worked in the last section. You give an extra power of t, so just multiply all terms in this group by a power of t that makes it clear of the ones over here. And that would just be t to the 1. Alright then, if this is yp is at e to the t, then we can start asking ourselves about the derivatives. Yp prime. And so the reason why, like I was going to say, the reason why this works is the same reason why it worked to do this in the homogeneous case. It's because basically when you have an extra piece of the derivative or of the differential equation being overlapping, then that causes it to essentially cancel when you put in an extra t. But let's just watch this happen in real time here. So a e to the t, once again we have to use the product rule, plus a t e to the t. So use the product rule, have a t be the first function, e to the t be the second. And then we just differentiate this term by term, so a e to the t stays unchanged, and then what we actually get here is just going to be another copy of the same thing that we produced just a second ago. A e to the t plus a t e to the t, by the same logic as led us from here to here, that would lead us from here to here. And so then yp prime, a double prime I should say, it's a double prime, it just didn't register. It's going to be 2a e to the t plus a t e to the t, which then, if we look back at the original equation, our yp double prime minus our yp, the zeroth derivative, is equal to e to the t. And we now just put the pieces each into play. So we're going to have 2a e to the t plus a t e to the t minus a t e to the t is going to equal e to the t. And so then what's going to happen here is we're going to have 2a e to the t, and these two terms basically cancel each other, and this is just going to equal e to the t. And so then 2a equals 1 if I divide by e to the t. And then that gives me a equals 1/2, which gives me yp equals 1/2 t e to the t, which gives me y equals c1 e to the t plus c2 e to the negative t plus 1/2 t e to the t. And so what we end up with in this situation is an extra term here, which represents the duplicated term, and the reason why it gets this extra t here is that deep in its construction, it is designed so that the extra t's will end up canceling from over here, and so then you end up getting something that has the same format as the original function. Okay, so this was a relatively innocent case of duplication, but now let's look at a much more nefarious case of duplication. So what we can also deal with by the same logic as what we've been doing, are actually applicable at higher than just degree 2 differential equations. They can be done even at degree 3 differential equations. So for example here, if I have the third derivative of y minus the second derivative of y is equal to 3 e to the x minus x squared, I can actually try to apply the same techniques in this higher degree case as I was in the lower degree case. So here, r to the third minus r squared equals 0 would be my characteristic equation, which would then be r squared times r minus 1 equals 0. Now r squared here will be will give us r equals 0 with multiplicity 2, and this one will give us r equals 1. Now if we look at what this is going to lead to, this is going to be from the r equals 0, 0, 0, 1. So this is going to give us a duplicated version of the e to the 0. So it's going to be c1 e to the 0t plus this is going to be the duplicated version, so it's going to be t e to the 0t plus this is going to be just c3 e to the t. So this is going to be our y complementary. So c1, and this just cancels and is just 1 really, plus c2t plus c, oh sorry, I mixed and matched my t's and x's again. Change all those x's up here to t's. Sorry about that. Supposed to be t's. T's throughout. T's for everyone. Okay, c3 e to the t. Now if I look at my f of t here, that's equal to 3 e to the t minus t squared. If I start taking derivatives of this, then I'll get 3 e to the t minus 2t. F double prime of t is going to be 3 e to the t still, minus 2. And f triple prime of t, since that's the highest derivative that we see in this equation, is going to be 3 e to the t, and then just a 0. So here, where we have seen these sorts of things, we can look at the different sorts of terms. in the derivatives of f, and we can see that we'll have terms of the form like a e to the t. So that's one family. And then we have another family that has terms of the form t squared, t, and just 1. So this is going to be bt squared, ct, and d times just 1. But when we look at this, there's a lot of duplication. So duplication, everything is duplicated. So duplicated. So this family, in order to clear it, I can get it totally clear by multiplying it by a power of t. So here, this one times t. So a power of t to the 1. So to clear duplication, so it's going to give us at, e to the t. Here, if I want to clear every member of this with every member of our original here, then what we're going to have to do is multiply it by at least a t squared, so that way even this one, even the lowest degree one, will be cleared of any duplication with the terms over here. So it's going to be b t to the 4th, c t to the 3rd, d t squared. And that will get us clear of any duplication. So this is to clear all duplication. So within each family, you just have to find the power of t that will clear all the members of that family from any duplication with the complementary solution. And then, what is that going to mean? It's going to mean that yp is going to be a t e to the t plus b t to the 4th plus c t to the 3rd plus d t squared, which means that yp prime is going to be, well, we've seen this kind of thing before, and we can tell it's just going to be a e to the t plus a t e to the t. This is going to be plus 4b t to the 3rd plus 3c t squared plus 2 dt. And then the second derivative, it's going to be a e to the t plus a e to the t plus a t e to the t. So this was me using the product rule there. Plus, now what are we going to have? We're going to have 12bt squared plus 6ct plus 2d. And if I combine like terms here, this is going to be then, so this is still second derivative, 2a e to the t plus a t e to the t plus 12bt squared plus 6ct plus 2d. Alright, and now finally it's time for the last derivative, the third derivative. We just need to take the derivatives up to the order of our actual differential equation here. So our differential equation involves the third derivative, so that's how far we need to go. So then what are we going to get? We're going to get 2a e to the t plus a e to the t plus a t e to the t plus 24 bt plus 6c, and then the d term will have disappeared. And this, once again, is 3 e to the t squared. Okay, so then our yp third derivative minus our yp second derivative is supposed to end up equaling 3e to the t minus t squared. I just left a bunch of space here so that these can be reasonably aligned when I insert the pieces into their respective spots. Okay, so what do we have here? We have 2a e to the t. Oh, I guess actually technically if I'm going to be simplifying this, I might as well put these together, so it's 3a e to the t plus a t e to the t plus 24 bt plus 6c. Okay. Alright, so then where does that leave us? So that's 3 a e to the t plus a t e to the t plus 24 bt plus 6c. Alright, and then that's all minus. Now we're looking at the second derivative, which is 2a e to the t plus a t e to the t plus 12 b t squared plus 6 ct plus 2d, and that's all equal to 3e to the t minus t squared. Alright, well now we can so if we're brave here, we can forego distributing this and then collect the like terms, but that seems risky. Let's just actually go ahead and multiply this out so that we don't make any mistakes. 3, or at least we minimize our chances of making mistakes. 3a e to the t plus a t e to the t plus 24 bt plus 6c, now minus 2a e to the t minus a t e to the t, which you'll notice that cancels that, and this will always end up happening. The terms that you create by adding extra powers of t will magically disappear from the left side of this equation when you do the subtraction of all the magic derivatives. It's just the way it is designed to work. Minus 12 bt squared minus 6 ct minus 2d is equal to 3e to the t minus t squared. Okay, so now let's look at the pieces. So this is a like term with this. which technically actually I could combine them, but before I go around separating things, but I am not going to rewrite the whole expression just to accomplish that. So e to the t. If I look at this, I've got 3a minus 2a equals 3 e to the t, which means that just a, just 3. So a equals 3. I was already just collecting coefficients here, so I didn't need that extra e to the t. Okay, what else do we have here? Let's take the t squared terms. So t squared terms. Let's identify all those. So that's going to be one right there and one right there. So it's going to be negative 12b is equal to negative 1, meaning b is going to equal 1/12. Okay, so duly noted, and now let's look at the t terms. So where do we have t terms? We've got 24b. We've also got minus 6c. And over here we don't have an e, so it's going to be 0. So what's this going to be? So this is going to be 24 times 2, or times 1/12. In other words, is going to equal to minus 6c equals 0. So that means 2 minus 6c equals 0. So that looks like c equals 1/3. Alright. So be it. And then for the constant terms, we've got 6c minus 2d equals 0. So I'll call that 4 underlinings. Just my way of indicating which terms were like which terms. Okay, so then what this means is, based on up here, 6 times 1/3 minus 2 times d equals 0. 2 minus 2d equals 0. So then d, I guess, equals 1. Alright, so now let's put all the pieces together then. So our general solution. Our general solution is going to be, now if we look back at what each letter was associated with, we can then put y equals, so we've got c1 plus c2t plus c3 e to the t plus a t e to the t, so it's going to be 3 t e to the t, and then the b was associated with t to the 4th, so it's going to be plus 1/12 t to the 4th plus 1/3 t to the 3rd power plus 1 t squared. Alright, so that's pretty much as bad as it can get as far as duplication and dealing with higher powers and things like that. But there's a note here. Again, I want to at least say this if we're not going to see an example of it. If we were given initial conditions y of 0 equals something, y prime of 0 equals something, y double prime of 0 equals something, we would have to take the necessary derivatives of our final answer, our general solution, set them equal to the given values, and solve for C1, C2, and C3. So that's what we would have to do if we were in the business of solving this for a specific initial conditions. Alright, so that is the method of undetermined coefficients. Now, it works out just great whenever we have a differential equation that fits the same pattern as what we've been doing. But what exactly was that pattern? Well, the most important thing about it was that our derivatives of f made up little families, and those families did not get out of control. They didn't. If we took derivative after derivative, we didn't end up producing more and more outlandish types of functions. So let's discuss what to do if you get a little bit more of a crazy system or a crazy equation where you can't get those nice little neat families of solutions. So it's called variation of parameters, this last method. The variation of parameters. So here's the problem. Sometimes the method of undetermined coefficients fails because the derivatives of f don't come in small well-behaved families. So in particular, the kinds of things that get us into trouble here are things like tangent or cosecant or things of that sort. So f of t equals like tangent of t, secant squared of t, things like that. So whenever you get something crazy like that, then when you start taking its derivatives, you start producing secant squareds. Then you start producing like secant cubed plus cosecant stuff, and it comes into crazy nonsense. And you can't produce the types of equations that we can solve for nice coefficients. So here's the idea of the variation of parameters. So we have another option. Alright, so here's the idea. So for variation of parameters, what we'll do is this. So if y1 and y2 are the two pieces, and we're just going to assume here this is this is going to be of order 2. Are the two pieces of yc, then leave off the c1 and c2 and look for a yp of the form yp equals a mystery u1 times y1 plus a mystery u2 times a y2, where u1 and u2 are functions, unknown functions, but they are going to satisfy a system of specific equations here. Satisfying the equations, and the reason why satisfying these equations will do the job is not something that we're going to fully vet out. We've been at it a while already, and it gets a little bit intricate. But if you are curious, you can be guided through the reasoning of this in the exercise in this section, number 27, I believe. It takes you through the full reasoning here. But essentially, this is the equivalent. This is the equivalent to basically finding a solution that satisfies the homogeneous part, and then the part that satisfies the non-homogeneous part. So u1 prime y1, u2 prime y2 equals 0, and u1 prime y1 prime plus u2 prime y2 prime is equal to f of x. Okay, so then for magic reasons, this turns out to work. Now then, we can rewrite the system as y1, y2, y1 prime, y2 prime times u1 prime, u2 prime, and that would equal f of t, or sorry, 0. This is going to be t again, 0 and f of t. Now, I want to remind you of a cool little fact from linear algebra, and that is what is called Cramer's rule. So there's a cool little formula for solving especially 2x2 equations called Cramer's rule here, which, so this is a linear algebra throwback. And it's called Cramer's rule. And the way it goes is that if we are looking for solutions of A, B, C, D, x1, x2, so just any system like this, equals EF, then x1 is equal to just the determinant of E and F in place of the first column, B and D. And then here, just leave the matrix alone, A, B, C, D. So where these represent the determinant. And x2 is very similar, just instead of replacing the first column, you replace the second column. So it goes A, C, E, F, divided by, again, just the original expression. Well, here, so here, what we'd have is then U1 prime would be the same as 0 y2 f of t y2 prime and all divided by y1 prime y2 prime. And u2 prime would be equal to this very similar expression, just with a different row replaced by 0 and f of t, and f of t. So we'd have here now y1 prime 0 f of t, the determinant of all that, divided by the determinant y1 prime y2 prime. Now, one note. The denominators of this, y1, y2, y1 prime, y2 prime, this is actually called, it has a name, it is called the Wronskian, or Wronskian, it's also pronounced. The Wronskian of y1 and y2. So in other words, w, y1, y2, or just w. So it is, it has a special name after a mathematician, Wronski, who was the first to name it and put it to use. And so then, what that means is, so u1 prime is just going to equal, and here in a second we'll actually just calculate this determinant, 0 f of t y2 prime over w, and u2 prime is equal to y1 prime 0 f of t divided by, once again, this Wronskian, or Wronskian. And this is now, let's just go ahead and calculate this. This is equal to, well, you just do 0 times y2 prime, and then minus y2 times f of t. This is negative y2 f of t divided by the Wronskian. And this one in turn will equal now, this is y1 prime, and then this one will be y1 f of t divided by w, and that's equal to u2 prime. Then, at last, we have the pieces that we will use to make our yp. So then, we can find yp equals u1 y1 plus u2 y2 by integrating. The above expressions. And so yp is equal to, so this is going to be, so it's going to be y1 times the integral, so it's y1 times u1, so it's going to be the integral negative y2 f of t divided by w dt. And then plus y2 times the integral of y1 f of t divided by w dt. And so finally we can just write this in its final format. So it's negative y1 integral y2 f of t over w dt plus y2 integral y1 f of t over w dt. And this is called the variation of parameters. Alright, well, let's give this a try. So let's try an example of this very process, and the example we'll take is going to have this form. Y double prime plus y is equal to cosecant squared x. Alright, so now we look at this formula here, we think about what we need to find. We need the y1 and y2 to begin with, and so that's going to involve us having to look at the characteristic equation and deal with that. Okay, so r squared to represent the second derivative, plus 1 to represent 1 times the zeroth derivative, equals 0. That's our characteristic equation. So then r squared equals -1, which means that r equals plus or minus I, which means then that yc, the complementary solution, is going to be of the form c1 cosine, so it's e to the 0 cosine of t, plus c2 sine of t, which means then y1 we'll just call for the sake of it sine, just because feels like that one should come first, and then y2 we'll just call cosine. Okay. Well then, let's look at the other pieces that we are going to need to deal with here. So now this is our cosecant squared t. I'm doing it in t. So f of t is equal to cosecant squared t. So let's try to remember what that even means. If you remember, cosecant is 1 over sine. So this is 1 over sine squared t. Good to know. Alright, well then, what is that going to mean? Well, let's first find the Wronskian here, and we can get to work. So if y1 is equal to sine t, and then y1 prime would be cosine t. y2, if that is cosine t, then y2 prime will be negative sine t, and that means then that the Wronskian is going to be equal to the determinant of the sine of t, cosine of t, negative sine of t, which is just going to equal, looks like negative sine t, so negative sine squared t, minus cosine squared t. In other words, if I pull out the negative, it's negative sine squared t plus cosine squared t, which is then just going to be negative 1. Okay. Now, let's think about the formula here. So according to our formula, our particular solution is going to equal negative y1 integral y2 f of t over w dt plus y2 integral y1 f of t over w dt. So now let's just figure out the pieces of this. So here we're putting in so this is y1, so let's see, y1 here is, this is negative sine negative sine t times the integral of y2 times f of t, so that's going to be cosine t times 1 over sine squared t divided by negative 1 dt. We'll sort that out in a second here. We're just getting it all on the page, and then we'll clean it up. Plus y2, which is cosine t, times the integral y1, which was again sine t, times f of t, which is 1 over sine squared t, all divided by w, which is negative 1. and that's an integral with respect to t. Alright, so now let's think about this. So those are going to cancel each other, and as for that, that's just going to come out to the front of that one. So let's see what we have here. So sine of t integral of cosine of t over 1 minus sine squared t dt minus cosine t integral, and it looks like here what we're going to have is sine over sine squared, which you may think it'd be nice to cancel, but let's just hold on that for a second. Sine squared t dt. Okay, so now let's think ahead a little bit about our strategy in trying to solve these, or trying to evaluate these integrals. So in this case, in the case of this first one here, oh wait, what am I doing? It's just divided by sine squared. What am I saying? It's nonsense. So cosine t over sine squared t. I don't know why I wrote that. I guess that -1 confused me, I don't know. Okay, but anyway, let's think about our strategy here. So the integral of cosine t over sine squared t dt. So I'll just call this integral number 1. So here, if I want to evaluate this one, I'm going to want to probably take a take a u substitution, and the u substitution that I think will work, and this u has nothing to do with any previous u1s, u2s, things like that. It's just a u substitution. It's going to be sine of t, meaning du would be cosine of t dt, which means then that I1 would equal, so it's again first integral, is just going to equal, it looks like 1 over u squared du, which is interesting. So then that's equal to the integral of u to the -2 du, which then we can actually evaluate. And by the way, for these we don't need plus c's, we're just trying to find u's that work. So then what's this going to be? Add 1 to the exponent and then bring 1 over that exponent down, so it would be u to the -1 and a negative. So it's negative u to the -1, and that means it's going to be -1 over sine t. Interesting. Alright, as for I2, so if I want to evaluate the integral of sine of t over sine squared of t dt, you may think, oh, the easiest thing here would be first to just cancel one of the signs from the top and the bottom, and that seems very reasonable. The problem with that is that it actually is harder than this original one. The easiest way to go about this next one is to do a little trig identity. So sine t, and then this would be 1 minus cosine squared t dt. And if you want to know, I think my subconscious was already thinking forward to that. Over here was what was going on. But anyway. So then, now, once again, I can think of this as being a u substitution. And if I do u equals now cosine t, then du will be equal to negative sine t dt. And so then the second integral here is just going to be equal to the integral of, looks like negative du for the top, and 1 minus u squared on the bottom. Alright, well then, so be it. Here, so then here, I can actually just break this up into partial fractions, but I'm going to bring the negative out to the front first. Or actually, yeah, this is what I'll do. This is what I'll do because I want my answer to fit the format that you're most likely to see if you do this by some other method. Okay, so then here, if I take a over, so let's just think about this for a second. So this is negative integral 1 over 1 plus u times 1 over 1 minus u du, which means then we can use partial fractions to evaluate this. So then what I can do is I can say a over 1 minus u squared is equal, 1 over 1 minus u squared is equal to a over 1 plus u plus b over 1 minus u. Then if I multiply everything through by the common denominator here, that's going to give me just 1 equals a times 1 minus u plus b times 1 plus u. And if I set u equal to strategic values, if I say u equals 1, for example, then 1 equals b times 2, which means b equals 1/2. If I say u equals u equals -1, then I'll have 1 equals, and this is going to be a times 2, and then that means again a is going to equal 1/2. So, choosing those strategic values for u, that gets me to the point where now I2 is equal to negative integral of 1/2 over, so let's see, the one that's over 1 plus u is what I called a, so it doesn't really matter, but 1 plus u plus 1/2 1 minus u du, which is equal to negative 1/2. And here I can just pull it, I can pull the negative 1/2 out to the front here, and that's going to give us, so it's going to be the integral of 1 over 1 plus u. So here, I'll just put it piece by piece here. And then plus the integral of 1 over 1 minus u du, which is equal to negative 1/2 times, and what we'll have here is just going to be equal to the natural log of the absolute value of u, and what we'll have here is going to, the natural log of the absolute value of 1 plus u. Yeah, let's just put that in. Negative 1/2 natural log of the absolute value of 1 plus u. This one, because of the chain rule, will get a negative, and so it'll be minus the natural log of the absolute value of 1 minus u. Alright, so what's that mean then? So putting these pieces together, then yp was equal to, so it was sine of t times I1, our first integral, minus cosine of t times I2. And so this is going to be sine of t times negative 1 over sine of t. And this next one is going to be minus, or actually plus, 1/2 cosine of t times the natural log of the absolute value of 1 plus u. And here u was equal to cosine t, minus the natural log of the absolute value of 1 minus cosine t. And so now we can do a little bit of cancellation here. And this first one is just going to equal -1, as we can see. As for this second one, what we can do here is use the properties of the logarithm to rewrite this as, so it's equal to 1/2 cosine t times the natural log of the absolute value of 1 plus cosine t over 1 minus cosine t, but this actually can be rewritten as 1 plus cosine t, 1 minus cosine t. If I multiply the top and bottom by the conjugate of the bottom, the kind of classic trig identity simplification move here, then what we would get is on the bottom, actually first I guess on the top, we'll have 1 plus cosine t, 2 copies of it, so it's squared. And on the bottom, we'll have 1 minus cosine squared t, which by the same identity we used a second ago is the same as 1 plus cosine t squared over sine squared t. And then that means I could rewrite this whole thing as 1 plus cosine t all over sine t, the whole thing squared, which I then in turn could rewrite as 1 over sine t plus cosine t over sine t all squared, which in turn I can finally rewrite as cosecant of t plus cotangent of t all squared. And this was just a chain of trigonometric reasoning to allow us to then simplify this a little bit more. -1 plus 1/2 cosine t, natural log, absolute value, cosecant t plus cotangent t squared, which then we can bring down this 2 and cancel with that. And this gives us equals -1 plus cosine t, natural log, absolute value, cosecant t plus cotangent t, and now the square gets canceled. Alright, so that will be our particular solution. So then yp equals that, -1, cosine t, natural log, absolute value, cosecant t, plus cotangent t. But then that also then gives us the full solution. Y is equal to c1 cosine t plus c2 sine t minus 1 plus cosine t times the natural log of the absolute value of the cosecant of t plus cotangent of t. So again, not the shortest and simplest method you've ever seen in your life. However, the alternative does not really exist actually for this problem. So if you wanted to solve this this problem by the method of undetermined coefficients, you would have to start taking the derivatives of the cosecant squared. And when you did that, you would be producing a bunch of crazy terms, and those crazy terms would not fall into a regular set of families for which you could assign generic coefficients in such a way that you were then able to actually solve and find the values of those coefficients. It turns out it's not going to work. This method, however, will work when you can actually integrate the integrals that it produces, which is not always as easy to do as it is to say, but when it can be done, this method can be used to solve the differential equations. Okay, well with that mammoth example, we will end this installment of Math 256. So you've got a lot to digest here. The method of undetermined coefficients, which has an easy version and a more difficult version, depending on whether there are duplications or not. And then finally, there is the variation of parameters, which can be done whether the yp can be found through undetermined coefficients or not. Alright, well, on that note, we're going to leave it there, and join you for the next episode of Math 256. Until then, bye!